Hello and welcome back to the tutorial on writing your own operating system. In this fifth part we will now really start talking to the hardware. As I said in the last video, if this is your keyboard and you press a key on the keyboard, then it will communicate with the programmable interrupt controller, which is between between the keyboard and the processor. As I said before, when you start your computer, the PIC is set so that it will not pass this information through to the CPU. We will have to talk to the PIC and tell it to give us this information. But if we told the PIC to give us this information, if we don't set up the interrupt descriptor table before, then it will give us this in form of an interrupt, but without this table, an interrupt will just create a general protection fault, and then I don't know what happens. I guess your computer will probably restart, or the virtual machine will probably just terminate, or whatever. So before we can tell the PIC to give us this information, we first have to set up the interrupt descriptor table. Okay. So what goes in the interrupt descriptor table? Well, an entry in there, of course it needs the information, what interrupt is this for? So an 8-bit integer, so a uint8t for the interrupt, the interrupt number. You know, when you press a key on the keyboard, you will get an interrupt 1, and also the timer in the PIC will give us an interrupt 0 in a regular interval. The interrupt number. Then we need an address in the RAM where to jump to. You know, if this is a RAM, then the code for the event handler for this interrupt is somewhere in the RAM. So we will have something like a void pointer to the handler. So the handler. And some flags again. Oh, and of course also the information. So we will have flags, and we talked about memory segments in the third video. We also need a segment. So this is going to tell the processor to switch to a certain segment before executing the handler. So this is, for example, if the processor is currently executing code in the user space and the handler is in the kernel space, then it needs to switch the segment to the kernel space. Okay, and you also need the access rights. Which is just a number from 0 to 3. 3 is user space, 0 is kernel space. So these are the things that will go in this table. Okay, now we have one problem. This handler here. I mean, in a C++ world, or actually in any higher level language, you would actually want to get this interrupt number basically as a parameter of some function, right? So you would want to write something like void handle interrupt and get the interrupt number as a parameter. right? So this is actually what we want. The problem here is, the CPU cannot, so to get this as a parameter, the CPU would have to push this number on a stack, and the CPU cannot make any assumptions about is it safe to use the stack. I mean, the stack might be set to something in the user space still, so it cannot push that to the stack. So what it has to do instead, and it might seem stupid at first, but really I don't think there is any alternative to this, is you need different handlers, so different code for every single interrupt. So here you would have one for interrupt 0, here you would have one for interrupt 1, and so on, right? So, and actually, how do you pass, or how do you get these addresses to put into the table entries, right? So, I mean, these interrupt handlers, the CPU is really in an uncertain state when you start, when you jump into there. So you should not really jump into a C++ function or anything, because C++, the compiler might decide to put stuff there which changes the registers, and this might really already screw up the code that you've been executing before. So so really we should write these handlers in assembler, and then again, like we did before, in the loader.s, we would jump into the my kernel in the kernel main CPP. So we would jump from assembler into C++, and we really should do the same thing here. So we will write these handlers, and actually we will automatically generate them with an assembler macro. And they are basically just pushing their number on the stack, and then jumping into such a C++ function, and from there we can continue going back into the object-oriented domain, right? So let's start doing that. So maybe start with this assembler code. So we'll have interrupt stubs.s, interrupts.h, and interrupts.cpp. Okay, so this interrupt stubs is mostly taken from the Tyndur project. I don't even know exactly how to pronounce it, but I've translated it to GNU assembler from NASM. So let's start here. Section text. Now we will have something. Maybe just have it start here. So. So here we will have a class called interrupt manager. And this class will have a public static function. Actually, it's going to return an 32-bit integer. And it will get the interrupt number as 8-bit integer. And the current stack pointer. So the assembler code is going to give us the current stack pointer, and in this interrupt CPP, it will for now it will just return the same stack pointer again. So this is really there to for task switching later. So there will be a timer interrupt which will give us a current pointer. We will store that away, and then take the stack pointer of some other process and return that stack pointer, so that after the interrupt, the CPU is executing the code of the other process. Okay, but for now we will just get the old stack pointer, and since we don't have multiple processes, we will return it again. And what I want to do here is I'll make a forward definition of printf, so that here we can do something like printf interrupt. Okay, so now if we compile this, and maybe we just do this actually. Okay, we need to include the types. And before I forget it, we also need to include the ports. Okay. Okay, and now we'll look into the this generated object file. So this is the name of the of this handle interrupt static method. Okay, so this is what it is called to the outside. I didn't want to name it to make it extern C. So so yeah, we will just copy this, and in the interrupt stubs put this here, so that now we can jump into that from this assembler file. Okay. Okay. Now inside this assembler file, we will have this int bottom jump target, and this jump target is basically giving this stack pointer. So push ESP, push the interrupt number, then call this this method like this, and then after that, we would actually have to pop the old pointer and interrupt number like this, 52.esp. So, but we don't actually have to do this. So this would this would actually clean up this stuff from the stack pointer. But since we overwrite the stack pointer immediately after that, with the result of the return value from the function, we can just skip this. So we do this instead. Okay, so this int bottom would basically just jump into the this handle interrupt function. Wait, we need to also have this interrupt number is a byte which is initialized to 0. Okay, so so this code will push these values on the stack and jump into this handle int. Now, as I've told you, we cannot simply do that because the contents of the registers might be important when we return from this event handler. So so before we can do this, we actually have to store away the old values of the registers. So we have to push all the registers and also push the data segment, ES, I think this is a frame pointer, GS. Okay. So we've stored this away now, and after we come out of this again, we need to restore these values from the stack. Okay, but in reverse order, of course, because it's a stack. So we take GS first, then FS, then ES, then DS, and then all the other registers, like this. Okay. And at the end of this, we need to tell the processor, okay, we are finished handling the interrupt, so you can return to what you were doing before. Or if we have switched the stack, then it will jump. It will work on the different process after that. So what we haven't done yet is we haven't set the interrupt number to anything yet. So and we don't actually have different jump labels for different interrupts yet, right? So So for this, I'm going to write a little macro. And interrupt request with one parameter. So this is going to publish to the outside this jump label called, it's very similar to this one. So interrupt manager, handle interrupt request, followed by this number that we get as a parameter. Interrupt request. This needs to become a 26 now. It's just the C++ syntax. And it has no parameters, like this. Okay, so this is the name. So in the interrupts.h we will have static void handle interrupt request, like this, and it doesn't matter, I think. Handle interrupt request 0x01, for example. This is going to be for the keyboard, and 00 is going to be the timer interrupt. And in this interrupt stubs, we will call this macro with the parameter 0x00 and also with 0x01. Okay, so this really creates the implementation of these two forward declared functions. Okay, so what do they do? They basically just move this this number into this variable, and then jump to int bottom. Okay, and then dot end macro. Okay, but this isn't all. This is for exceptions. So this is handle for exceptions. Handle for exceptions. This must be a 19. Okay, and the interrupt request will add to the number also the content of a compiler variable IRQ base, which we set to to 32. 0x20. Okay. Yes. So this looks good now. And of course, for more interrupts, you would just copy this several times, okay? So, so now this, I think this should complete these interrupt jump targets. So now we need to construct the interrupt descriptor table, and yeah, the entries are called gate descriptors. So so we will have a nested class again, or a struct in this case. And this needs to be byte perfect again, so we give this attribute packed again. Okay. What goes in here? uint 16 t. Yeah, this is again like the entries in the global descriptor table. So we have the address of the handler, and this is again split. So handler address low bits. Then we have the offset of the global descriptor table. For the code segment. One reserved byte. Then the access rights. And the high bits of the handler address. Okay. And then for this structure, we will create an array with 256 entries. Static gate descriptor. Okay. Then we will have a constructor for this interrupt manager class, which this will get a pointer to the global descriptor table. So we will also have to include gdt.h. So it will get global like this. And a destructor. And it will also get a static function which sets the entries in the interrupt descriptor table. Okay. Again, what are the parameters for this? Well, uint 8. The interrupt number, of course. Yeah, basically just the things for this that are in this structure. So interrupt offset. Yeah, then the pointer to the handler. Then uint 8t. Oops, what happened? So basically the access rights and uint 8t for basically the flags. Okay. And we need another function here. Ignore interrupt request, like this. Okay. What was all this? We need to set so we need to implement these three methods and also instantiate this table, right? Because it's a static member. Okay, so in the constructor we will first set all the entries to this interrupt ignore method. Okay, so every interrupt that we don't set explicitly just should be ignored, okay? Because if it isn't, then we get a problem. So if we get an interrupt and we don't have a handler for it, we get a global protection fault and the operating system crashes, okay? So okay. So here's a the table. Then how do we set these entries? So the handler address low bits this isn't surprising, we just take the low bits of the handler address. Like this. Then the high bits. Almost the same. Let me shift them 16 bits first, okay. The code segment selector is just copied from the parameter. The reserved byte is just always 0. Now we only need to set the access rights. So here we combine this constant with the descriptor type. From the parameter and also with the privilege level. But this is shifted by 5. And we only need the last 2 bits of this. You know, this is a number between 0 and 3, so we can do it like this. Okay, so this is to set an entry in the table. And now the constructor of the interrupt manager will basically set these entries. So this was called like that, wasn't it? Yes. But this should be a uint 16. Okay. Okay, and now we will just set these entries in a loop. So for the ith entry, we take the code segment from the global descriptor table. The address of the interrupt ignore function. Privilege level 0, so kernel space, and the type is interrupt gate. Okay. Now we have initialized everything with something sane, and then we can create two explicit entries for 0x20 and 0x21. You know, we are creating these handlers with 0x00 and 0x01. But we will get this number increased by this 0x20, okay? So that's what I'm doing here. So code segment, then handle interrupt request 0x00. Okay. So if we get an interrupt 20, or let's say if we get an interrupt 21, or 0x21, it's actually interrupt 33 then, we will jump into this handle interrupt request 01. So this one, which is a copy of this, which will give us this 0x20 plus this 0x01. So we will get a 0x21 pushed when we jump into this handle interrupt function. Okay. So this sets the interrupt descriptor table, and now we need to tell the processor to use this. So what I'll do is here I will have another nested structure. Interrupt descriptor table pointer. Again with attribute packed with a uint 32t base, which is the address of the table, and uint 16t for the size. Okay. So after I've created the table, I can now tell the processor to use it. So interrupt descriptor table. The size of the table is 265 because we have 256 entries times the size of a gate descriptor and -1. So this is a pointer to this table, right? Like this. And then we need to tell the processor to load the interrupt descriptor table into 0. Like this. Whew. Okay, so what we have done now is we have created the table and we have told the CPU to use this. What we haven't told the CPU yet is to actually start sending these interrupts. So what we need to do next is we'll have another method here. And here we basically just say asm start interrupts. And the reason why this is in a different method is because in the kernel we will have the interrupt descriptor table or an interrupt manager. Which gets the global descriptor table as parameter. So the reason why we have this as a separate method is because we will first instantiate the table, then we will instantiate all the hardware and activate the hardware, and after that we will activate the interrupts. So when we instantiate the hardware, we already need to have the interrupt descriptor table so that the hardware can so it can tell the interrupt manager, hey, I want to handle interrupt 20 or whatever. Okay, so let's see what happens if we compile this. Okay, this kind of works, but doesn't accept these functions that we've created in assembler. Yeah. Okay, of course, we just declared the jump target, but we didn't actually put it there. Okay. Okay, this has the wrong case. It should be uppercase here. Okay, the only thing left is the ignore interrupt request. Okay, then without the 4 bytes there, this should be 22. Okay. Let's see. Yes, now it worked. Okay, so now we have the interrupt descriptor table. We are telling the CPU to use it. So at this point we have the table. The CPU knows that the table is there, but we haven't told the pick to send interrupts yet. Okay, so this is really the last step we need. We need to tell the pick, give us the interrupts, because everything is set up now. We are now ready to get these interrupts. Okay. So how do we do that? So in the interrupt manager, we already have the port. So the first thing we need is the ports for the communication with the pick. So port 8-bit slow. One thing, by the way, that I haven't mentioned yet is we don't actually have only one pick. We have two different picks. So a master pick and a slave pick. And a slave pick. And we need to communicate with both of them. So we have one port for commands, one port for data. A slave port for commands and a slave port for data. Okay. Now. When we instantiate the interrupt manager, then we first need to instantiate these ports. The master command port is 0x20, the port number 0x20. Pick master data is the port 0x21. The slave commands are on A0 and slave data is A1. Slave data, slave command. Okay. Now, before we tell the processor to use this interrupt descriptor table, we communicate with these picks. X11, 0x11. So here we tell, so as I've told you, if you press a key on the keyboard, you will get an interrupt 1. The problem is that the CPU uses interrupt 1 internally for exceptions also. So what we are doing now is basically we are telling the master PIC, if you get any interrupt, just add 0x20 to it, and the slave PIC is told to add 0x28 to it. Okay, so because both of these PICs have 8 interrupts that they can use. So this is 20 to 27, and then this is 28 to 30 in hexadecimal. Okay. And then this is some initialization. I think this tells the master, you are the master. This tells the slave, you are the slave, I think. Okay. Let's see. So, what happens if we run this? Yeah. We are getting an interrupt. We are getting an interrupt. Do you realize what that means? That means that we just have received the first actual response from the hardware. So, as you can see, we only get one interrupt right now, but actually the timer interrupt should give us more interrupts. And the reason for this, why we only get one right now, is because we haven't told the PIC, yeah, thank you for the interrupt. I have finished working with this. So the handling of this interrupt is finished. Okay, so we also need to do that, but we'll do that in the next video. Okay, so we have really spent enough time today. So tune in next time when we will answer these interrupts, and then we will actually communicate with the keyboard and get actual key strikes from there. Okay, so tune in next time and subscribe so that you don't miss the next video. See you next time.